Foundation models are transforming medical imaging, but they consistently hit a wall when deployed outside their training distribution. In mammography, a model that performs flawlessly on one hospital's data can fail dramatically on another's. This isn't just a data quality issue. It's a fundamental challenge of out-of-distribution generalization. Today, we're breaking down a rigorous new benchmark that evaluates 15 foundation model backbones across 15 datasets from 12 countries, 3 distinct clinical tasks, and reveals a counterintuitive truth. Mammography-specific pretraining alone does not guarantee robustness. In fact, a vision-only model trained entirely on natural images remains one of the strongest baselines. Let's examine exactly how they measured this, what the data shows, and what it means for clinical AI deployment. To isolate representation quality from task-specific tuning, the researchers built a unified benchmark using a frozen backbone linear probe protocol. They evaluated models across 3 clinically distinct prediction tasks: image-level breast density classification, exam-level BI-RADS assessment, and exam-level cancer status. Public datasets use wildly different annotation schemes, label granularities, and clinical workflows, so the team first harmonized the labels and standardized preprocessing, resizing everything to 1024 by 768 pixels to preserve global breast context. They then froze the pre-trained encoder completely and trained only a lightweight, task-specific classifier on a single source dataset. The real test comes when that classifier is evaluated on external, out-of-distribution datasets. The models were grouped into 5 families: natural image self-supervised learning like DINAV-2 and DINAV-3, general radiology SSL, mammography-adapted SSL, general medical vision language models, and mammography-specific VLMs. This setup ensures we're measuring how well the underlying representations generalize when the data distribution shifts. The results immediately highlight a critical gap between in-distribution and out-of-distribution performance. When plotting ID AUROC against mean OOD AUROC, you see a consistent downward shift. For BI-RADS, the rank correlation between ID and OOD performance is strong, but models still drop by nearly 9 percentage points on average. Density shows an even higher performance ceiling in distribution, with many models pushing past 90% AUROC, yet the OOD drop remains stubbornly consistent. Cancer status is the noisiest task, largely because label definitions vary drastically across datasets. Some use BI-RADS-derived proxies, others rely on direct biopsy confirmation, and severe class imbalance skews the metrics. But here's where the findings get interesting. Mammography-specific vision language models, specifically MA and Mammo-FM, consistently top the overall OOD rankings. They leverage clinical language alignment, which appears to anchor their representations to meaningful medical concepts. However, the standout surprise is DINAV-3. Despite being trained entirely on natural images with 0 medical or mammography exposure, it remains a fiercely competitive vision-only baseline. It outperforms several models that were explicitly fine-tuned on mammography datasets. This tells us that strong visual feature extraction from large-scale SSL pretraining can sometimes outperform narrow domain adaptation, especially when that adaptation is limited to a single dataset and doesn't change the underlying pretraining objective. This leads to a crucial insight. Mammography exposure alone does not guarantee robust OOD generalization. When the team examined mammography-adapted SSL models like DINAV-3 Embed or Versa Mammo, they saw marginal gains at best, and sometimes performance degradation on BI-RADS and cancer status compared to their natural image counterparts. The pretraining objective and data diversity matter far more than just seeing mammograms. When we drill down to the dataset level, the picture becomes even more nuanced. Average OOD scores mask severe heterogeneity. For example, Mammo-FM dominates on datasets like CDD-CESM and CBI-SDD-SM, which feature non-standard modalities like contrast-enhanced or scan-film mammography. But MA consistently outperforms it on density prediction across the board. Why? Because MA's pretraining explicitly used tabular metadata, including density labels, to generate text reports. Mammo-FM, on the other hand, was trained on actual clinical reports, which focus on outcomes like BI-RADS and cancer status rather than explicit density annotations. This difference in supervision signal directly shapes what the model learns to prioritize. It's a clear example of how pretraining data curation dictates downstream robustness and why aggregate scores can be misleading. To understand what's actually happening inside these representations, the researchers ran a UMAP dimensionality reduction on the frozen features. What they found challenges a common assumption in medical AI. You don't need complete domain invariance to achieve robust generalization. Across all models, dataset structure, manufacturer, view position, and even BI-RADS scores remain visibly organized in the embedding space. Changing the pretraining source reshapes the geometry, but it doesn't erase clinical signal. For instance, MA shows the clearest density separation in the feature space, which aligns perfectly with its top density AUROC. Yet it still preserves view separation, likely because its language pretraining explicitly referenced image metadata like view and side. Conversely, Mammo-FM shows better multi-view alignment, probably because its clinical reports describe patient-level findings without encoding rigid image-level metadata. These feature space insights prove that useful representations don't have to be domain agnostic. They just need to preserve the clinical signal that matters for the task, while gracefully handling acquisition variability. So what's the bottom line for foundation models in mammography? First, strong in-distribution performance is a poor proxy for real-world utility. Second, domain-specific pretraining is valuable, but it's not a silver bullet. If it's limited to a single dataset or optimized for the wrong supervision signal, it can actually hurt generalization. Third, vision-language alignment provides a meaningful edge, but high-quality natural image SSL encoders like DINAV3 remain incredibly difficult to beat without careful task-specific tuning. The field needs to move beyond aggregate benchmark scores. Robustness is heterogeneous, and evaluation must happen at the dataset level, with explicit attention to label provenance and acquisition variability. This study also highlights important next steps. Linear probing measures representation quality, not absolute task performance. Future work needs to explore full fine-tuning, uncertainty calibration, and confidence estimation across OOD distributions. Because in clinical deployment, knowing when a model is uncertain is just as important as knowing what it predicts. If you're working on medical AI, foundation models, or domain generalization, this paper provides a rigorous, data-driven framework for evaluating what actually works when the real world shifts. The full codebase and benchmark details are publicly available, so dive in, test your own models, and help push clinical AI toward truly robust deployment. Thanks for watching.